This is Lab 3 Black Hole Orbit. In this lab, we are given position data over time of a star of specified mass as it orbits around a black hole. We were to calculate the mass of this black hole through the application of Newton's law of universal gravitation and Newton's second law. We assume that the only force acting on the star is gravity, and by using Newton's universal law of gravitation, we can rearrange the equation to solve for the mass of the black hole, m2. This is possible because we already know the values for g, the gravitational constant, m1, the mass of the star, r, the distance between the star and the black hole, and we can calculate a value for Fnet. To calculate the Fnet value, we turn to Newton's second law, which tells us that Fnet is equal to dp dt. dp dt stands for the change in momentum over the change in time. These two things can be broken into their parallel and perpendicular components. I'll come back to this in a moment. Looking at my Python code, we can see that the mass of the star equals 5.0850 times 10 to the 27th. Delta T equals 86,400 seconds. These two values are given on WebAssign. Here, T equals 0, indicating that we are starting at time 0. After importing the given star position data, we calculate the velocity of the star at the beginning and end of a specific time interval. This is represented below as v initial and v final. These velocities are then used along with the mass of the star to find p initial and p final. These represent the initial and final momentums of the star. When we run the code, you see that the path of the star is indicated by the green line. The yellow arrow represents the net gravitational force between the star and black hole. The parallel and perpendicular components of that force are represented by the black and blue arrows respectively. To find the individual components of the gravitational force, I used this loop. As I stated before, the components of dp dt are equal to those of Fnet. To find the parallel component, we need two things, a magnitude and a direction. Since this is the parallel component, its direction, by definition, is equal to that of the net momentum and is represented by p hat here. Now to get a magnitude, represented by d mag p dt, we take the change in momentum divided by the change in time. Finally, we multiply d mag p dt by p hat to get dp dt parallel. To get the perpendicular component, dp dt perp, we simply subtract dp dt parallel from our net dp dt. Down below, the arrow scales were adjusted to ensure that the lengths of the arrows, which represent the magnitudes of the forces, were proportional. As I said before, these items are equal to each other. This is only partially true. The magnitudes of these things are equal. However, F and dp dt describe different things. Fnet describes the force on the system, while dp dt describes the change in momentum over a time interval. So Fnet and dp dt are related, but they are not the same thing. This question asks if the black hole was to be replaced by a different black hole at the same location, and the time interval and motion of the star remain unchanged, if it would be possible for the black hole to have a different calculated mass than that of the original. The answer is no. If we look at the universal law of gravitation and rearrange it to solve for m2, the mass of the black hole, then we see that all other variables are not changing. Therefore, the mass of the black hole must have the same value as it did before. Thanks for watching.